Hi, in this video we get acquainted with vectors and vector algebra. In computer graphics we get the computer to do geometric calculations. The computer is able to work with numbers, so we really need this algebraic framework to develop computer graphics. Let's see what we have after establishing the axioms. We have points and lines, and every 2 points define a line, and 2 lines may intersect in a point. If we had a non-metric geometry, like the projective geometry, basically that would be it, which we may call as geometry or universe. In metric geometries, however, we have two additional important concepts. We have the ability to determine the separation of 2 points by assigning a distance to them, or the separation of 2 lines by assigning an angle to them. Angles give us the notion of direction. Distance and direction will be really important to us, so we introduce a new actor in our geometry universe called the vector. The vector encodes direction and distance for 2 points. We may also say that a vector is a translation that translates the first point to the second one. So originally, we assign vectors to pairs of points. If we fix one of the 2 points and call it the origin, then single points will be identified by vectors unambiguously. And in this case, we call the vector associated with a point the position vector of that point. So with matrix or geometry has numeric properties, we can assign a distance to 2 points of our geometry, or alternatively the length of the vector between the 2 points, and we can also measure the separation of 2 lines by computing the angle of the 2 vectors pointing into the direction of the 2 lines. This is not the only possibility to establish a connection between geometry and real numbers. For example, we can say that for different real values interpreted as, for example, the time, or location is at a different point of our geometry. In this way, we can describe motions or one-dimensional subsets of our universe. The functions mapping real numbers on points can be not only one-variate but also multivariate functions where two-dimensional subsets, for example, can also be defined. The mapping can be defined in the reverse direction as well, and we can assign real numbers to points. For example, we can assign the temperature to every point. Finally, we can introduce functions that map points to points, and we call them transformations. So in this extended metric universe, vectors play an important role. Algebra means a set, the set of factors in our case, and operations that can be executed on this set. So let's see what kind of operations can be defined on vectors. As vector is a translation, it makes sense to execute 2 translations one after the other, and the operation is called the addition of 2 vectors. We can determine the result of vector addition by simply constructing a parallelogram and obtaining the diagonal of that parallelogram where the 2 sides are just the 2 vectors to be added. As the parallelogram has the property that the edges on the opposite sides are equal and parallel with each other, it can be seen that vector addition is commutative operation, so I can exchange them in the operation, the result will still be the same. And even associative operation, so parentheses can be reorganized if more than 2 vectors are added. Similarly to addition, we can also define subtraction, which is just the other diagonal of the parallelogram, and the inverse operation of addition, we also have scaling operation, which means that the direction encoded by a vector doesn't change, but we just modify the distance encoded by the vector. Scaling is distributive over addition, so if we scale a sum of two vectors, the result is equal to the sum of the two scaled versions of the original operand. There are more exciting operations as well. For example, the dot product of two vectors, also called the scalar product of two vectors because the result is a real number, a scalar. So the definition is the scalar product of two vectors v1 and v2 is a number that is equal to the product of the lengths of the two vectors multiplied by the cosine of the angle in between the two vectors. This operation has interesting geometric meaning, namely dot product is a projection. When we project vector v1 onto vector v2 and scale up the result with the length of v2. Concerning the properties of the dot product, it is not associative. However, it is commutative, and this is obvious from the definition because if we exchange v1 and v2, the multiplication of real values is commutative, and the angle between two directions doesn't change if we exchange the two directions. Very importantly, the dot product is distributive with the addition, so when we multiply a vector with the sum of two other vectors, the multiplication can be done individually for the terms of the sum. The proof of this property is based on our intuitive interpretation of the dot product, namely that it is a projection. Indeed, if we have two vectors and project them onto a third vector, the result will be the same when we project the sum of the two vectors or project them individually and add up the two projections. Dot product can replace measurements in our geometry. Measurements that aim at distance and angle calculations, because if we know how to evaluate the dot product in our geometry, we can obtain these numeric properties. For example, if we multiply a vector by itself, then the angle is 0, so the product is just the square of the length of the vector. Dividing a vector with its length, we obtain a vector that shares the direction of the original vector but has unit length. Such vectors are called unit vectors. If we divide the dot product of two vectors with the product of the lengths of the two vectors, then according to the definition of the dot product, we can express the cosine of the angle between the two vectors. Finally, we can determine whether two vectors or two directions are orthogonal to each other by checking the result of the dot product. If the dot product is 0, then the two directions are orthogonal because cosine 90 degrees is just 0. In addition to the dot product, we have another product as well called the cross product, where the result of multiplying two vectors is a vector. The definition is the following. The length of the cross product of two vectors is equal to the multiplication of the length of the two vectors multiplied by the sine of their angle. Concerning the direction of this vector, this direction is orthogonal to the two operand vectors, and as there are two orthogonal directions, we have to obtain that one where our third finger points when our thumb points into the first vector and our pointing finger points into the direction of the second. This is called the right-hand rule. The cross product also has interesting geometric meanings. On the one hand, the cross product is the area of a parallelogram, and the direction of the result is just orthogonal to the plane of the parallelogram. On the other hand, cross product is also a projection, similarly to the dot product. However, no, the projection is organized differently. So we project vector v1 onto the plane that is perpendicular to v2. After projection, we apply a 90-degree rotation and finally scale up the resulting vector with the length of v2. Let's see the properties. The cross product is not associative. It's not even commutative. In fact, it's alternating, which means that if we exchange the two operands, a negative sign should be introduced. But cross product is also distributive. So when we multiply a sum, the terms can be multiplied individually and the partial result summed. The proof that cross product is distributive is based on our geometric interpretation because again, cross product is a projection and we have seen that projection is distributive operation plus a 90-degree rotation, and rotation is also a distributive operation, and finally a scaling, and scaling is a distributive operation as well. We introduced subtraction and scaling for vectors. If we can subtract and scale, then we can also derivate. Because in the formula of the derivative, only these two basic operations show up. Let us assume that we have assigned a scalar value for every point in our geometry. For example, we assign the temperature. To visualize such a function over the two-dimensional plane, we can use the visualization of level lines. This type of visualization is quite popular in maps where points having the same scalar value are connected and we add the scalar value associated with this curve, also called level curve, because the scalar has a constant value on this curve. Let's consider point R star. And let's move a little delta s in direction of unit vector v0. So we shift our original point to arrive at this red point where the temperature can be fetched again. So the scalar value in the red point is here and the scalar value of the original point is here. We can compute their difference. And if this difference is divided by the length of the vector, that is the distance between the original and shifted point, then we will have a formula which looks like a differential. Of course, we obtain the derivative if this delta s goes to 0. This derivative is called the directional derivative, because in this derivative, direction v0 plays an important role. When computing the directional derivative, we can consider all possible directions. From these possible directions, we identify one, which is called the gradient, where the rate of change is maximal. So, by definition, the gradient is a directional derivative with maximum change of rate. The gradient has the property that it is always perpendicular to the level curve. To see this, let us assume that we move into a direction that is not perpendicular to the level curve. And this direction can be decomposed to a tangent direction and a direction that is perpendicular to the tangent. Moving in the tangent direction is not really efficient in order to increase the rate of change because on the level curve nothing changes. The scalar value is constant. We can obtain the maximum rate of change if there is no movement in the tangent direction. So the selected direction is just perpendicular to the tangent. We can also introduce another derivative of the function that maps real numbers on the points of our geometry. Let us use the analogy that we are at different points for different points of time t. So when the time is t star, we are here with respect to the origin, and a little bit later in t star plus delta t, we are here in this new point. During the time interval delta t, we moved between these 2 points. So the translation executed in time delta t is just the difference of the position vectors of the 2 points. If we divide this difference with the time needed to make this motion, we get a differential-like expression for which delta t should go to 0 to obtain a real derivative. This derivative is the parametric derivative of our location, and if t is the time, this is just the velocity of our movement. We know from physics that this velocity is always tangent to the curve of our path. With the introduction of vector operations, we are ready to define the coordinate system. We will use several coordinate systems in this subject, but the most important one will be the Cartesian coordinate system, named after René Descartes, who was a mathematician, philosopher, and also mercenary. The Cartesian coordinate system is a pair of vectors I and j, where both vectors are unit vectors and they are orthogonal to each other. Using the language of vector algebra, it means that if we multiply I with itself using the rules of dot product, then we get 1. Similarly, j.j is also 1. However, I.j and j.I are 0 because of orthogonality. With these two unit basis vectors, any point on the plane can be expressed as a linear combination of these basis vectors, where factors x and y are called the Cartesian coordinates. Cartesian coordinates are unambiguous, because if we have a vector r, then we can express x and y unambiguously. This expression is nothing but the projection of r onto the two coordinate axes. We can also use the derivatives. So for example, if a point moves in time so that x is in fact the time, then the velocity vector of that point is I. And similarly, if y is the time, then the velocity vector is j. I and j basis vectors can also be obtained as gradients of coordinates x and y. It means that basis vector I is in fact the direction in which x changes with the highest rate. If there is a one-to-one correspondence between vectors and coordinate pairs, then all operations can be evaluated in coordinates as well. So let's see how it can be done. The first operation is addition. So we express the two vectors that are added as linear combinations of the basis vectors with the coordinates, and then we exploit the associative property of vector addition and also the distributive property of scalar multiplication. So this sum can be rearranged in the following form, which means that we can add two vectors by adding the coordinates independently. Let's see the dot product. Again, we express the two vectors. Then we exploit the distributive property of the dot product. A term from the first factor should be combined with every term of the second factor. We will have x1 times x2 times I dot I is 1. Then x1, y2, I dot j is 0, so this term doesn't show up in the result. y1, x2 times j dot I is again 0, so we can ignore it. And finally, y1, y2, j dot j is 1, so we will have y1, y2 in the result. Two vectors are multiplied with the rules of the dot product by multiplying the coordinates independently and then adding up the results of the coordinates. The length of a vector is just the square root of the multiplication of the vector with itself. Using the previous result, how to compute the dot product, the multiplication of a vector with itself is just x squared plus y squared, from which we should compute the square root. Let us note that this is nothing but the theorem of Pythagoras. So let's appreciate the power of vector algebra. We obtained the proof of the Pythagoras theorem for free. What about the gradient? The gradient is a directional derivative in a direction in which the rate of change is maximum. So let's evaluate the directional derivative in the unit vector direction Vx and Vy. We have to apply the chain rule for multivariate functions, and it works in the following way. First, we have to compute the derivative with respect to the first variable, so with respect to x, and multiply the result with the derivative of the inner function. So if we derive this function with respect to s, we get Vx. The same operation should be repeated for the second variate. F should be derived with respect to y and then multiplied by Vy. Vy is just the derivative of the inner function with respect to s. Looking at this formula, we can realize that this has the same structure as the dot product. So it can also be imagined as the dot product of a vector containing the partial derivatives of f and or unit length vector specifying the direction. So this is the formula for directional derivative. We have to find that direction in which this directional derivative is maximal. The directional derivative is a dot product. We know that the dot product is equal to the absolute value of the first vector, which is independent of the direction, multiplied by the absolute value of the second vector. The second vector is a unit vector, so this absolute value is 1, and 1 is obviously independent of the direction. And finally, we have to apply a multiplication with the cosine of the angle in between the vector of partial derivatives and the vector of v0. The cosine function has a maximum when the angle between the two vectors is 0. So the gradient, which has an absolute value and also a direction, so it's a vector, is equal just the first vector in this dot product. We have one more operation left, the cross product. Since the cross product is usually interpreted in 3 dimensions, I immediately give the formula for 3 dimensions, which means that in addition to basis vectors I and j, we also use a third basis vector k that is also a unit vector and perpendicular to the other 2 basis vectors. So the 2 vectors are expressed in the form of Cartesian coordinates. Then we exploit again the distributivity of the cross product. So the product can be evaluated term by term from the left and from the right factors. So the first partial product is x1 times x2 times I cross I. However, I cross I is 0, because in the cross product we have the sign of the angle between the 2 vectors. And if 2 vectors are parallel, this angle, so is the sign, are 0. The second term is x1 times y2 times I cross j. I cross j is k, so we will have a term in the result here. And if we continue this and consider all the possible terms, we obtain this nice expression, which can be remembered as a determinant, where the first row contains the I, j, k basis vectors, the second row the 3 Cartesian coordinates of the first vector, and the third row the 3 Cartesian coordinates of the second vector. And this concludes our short section on vector algebra. In the next video, we will continue with analytic geometry, considering not only Euclidean but also other geometries as well. Thanks for your attention.